While evaluating integrals, we often come across situations where the integrand is a fraction of polynomials. Such integrals can be evaluated by a special criterion. Let's see what it is. First, check whether the function is a proper fraction. If the degree of the numerator is less than that of the denominator, then it is a proper fraction. Let's consider an example. Here, the degree of the numerator is 2, while the degree of the denominator is 3. Thus, the degree of the numerator is less than the degree of the denominator. Hence, this is a proper fraction. If the function is a proper fraction, then check whether the denominator can be factorized into linear or quadratic factors. If the denominator cannot be split, then other integration methods are chosen. If the denominator can be split, then split the function into partial fractions. We will shortly discuss the ways to split a function into partial fractions. If the function is not a proper fraction, that is, the degree of the numerator is greater than or equal to that of the denominator, then it is an improper fraction. Let's consider an example. Here, the degree of the numerator is equal to 4, while the degree of the denominator is equal to 2. Thus, the degree of the numerator is greater than the degree of the denominator, and hence it is an improper fraction. In such cases, we convert the function into a proper fraction by dividing the numerator by the denominator. Here, P1 of x upon Q of x so obtained is a proper fraction. After this, we check whether the denominator of this proper fraction can be factorized into linear or quadratic factors. If the denominator can be split, then split P1 of x upon Q of x into partial fractions. For example, if P of x upon Q of x is an improper fraction, as shown here, then to convert it into a proper fraction, divide the numerator by the denominator. After the division, we get this expression. Here, T of x is equal to 3x squared plus 8. P1 of x is equal to 30. Observe that now, P1 of x upon Q of x is a proper fraction and can be split into partial fractions. This is how we convert an improper fraction into a proper fraction. Now, split the function into partial fractions. Now, let's concentrate on how we split a proper fraction into partial fractions. The table lists some standard functions that we will encounter. Observe that each rational function in the table is split into partial fractions with constants like a, b, and c. Let's find the intuition behind this splitting. Consider the first rational function px plus q upon x minus a into x minus b. This can be written as a upon x minus a plus b upon x minus b. We take the LCM on the right-hand side. Since the denominators are equal, we can equate the numerators on both the sides. On rearranging the terms on the right-hand side, we get px plus q is equal to a plus b into x minus a into b plus b into a. On comparing the coefficient of x on both the sides, we get P is equal to A plus B. Let this be equation 1. On comparing the constants on both the sides, we get Q is equal to minus of A into B plus B into A. Let this be equation 2. Now, we will solve equations 1 and 2. Multiply equation 1 with B and add this to equation 2. This is done as shown. This gives B is equal to BP plus Q upon B minus A. Similarly, we multiply equation 1 with A and add to equation 2. This gives A is equal to AP plus Q upon A minus B. This is how we find the constants A and B. Similarly, the constants in the other expressions can also be found. Now, let's solve an example. This is a rational function in which the degree of the numerator is less than the degree of the denominator. Hence, it is a proper fraction. Rewrite the denominator in the form of its factors. On factorizing, the denominator of the integrand can be expressed as the product of the factors 3x minus 5 and x minus 5. Now, the integrand is of the form px plus q whole divided by x minus a into x minus b. So it can be written as a upon x minus a plus b upon x minus b. Let us denote this by equation 1. Take the LCM on the right-hand side. This makes the denominator equal on both the sides. So, the numerators can be equated. On comparing the like coefficients and constant terms, we get a plus 3b is equal to 2 and minus 5 times of a plus b is equal to 3. On solving the equations, we get a is equal to minus 19 upon 10 and b is equal to 13 upon 10. Now, from equation 1, the given integral can be written in terms of partial fractions as shown. Substituting the values of a and b, and then integrating each integral on the right, we can easily evaluate the given integral. Therefore, the solution is equal to minus 19 by 30 into log mod of 3x minus 5 plus 13 by 10 into log mod of x minus 5 plus c. Let us look at another example. Here, we will evaluate integral of 7x minus 4 upon x minus 1 whole squared into x plus 2. This is a proper fraction, since the degree of the numerator is less than that of the denominator. Split the integrand into partial fractions. Taking LCM on the right-hand side, we get the denominators on both the sides equal. Hence, the numerators can be equated. Simplify the expression on the right-hand side of the equation. On comparing the coefficients of x square, we get a plus c is equal to 0. Comparing the coefficients of x, we get a plus b minus 2c is equal to 7. Comparing the constants, we get minus 2a plus 2b plus c is equal to minus 4. On solving equations 1, 2 and 3, we get a is equal to 2, b is equal to 1 and c is equal to minus 2. Therefore, the given integral in terms of the partial fractions can be written as shown. Now, evaluate each integral on the right-hand side as shown. On simplifying, we get 2 times of log mod of x minus 1 upon x plus 2 minus 1 upon x minus 1 plus constant c.